non-supersymmetric gauge theory, in particular QCD, and most recently has done a bunch of very interesting work on Chern-Simons and related topics. So I think he'll tell us something about that work today. So Avner, thank you very much. Please feel free to start.
Thank you very much. So the talk today will be based mainly on this new paper that just appeared yesterday on the archive, but some of the ideas already appeared in the previous paper from March about Chern-Simons. So, what is it? And I will start from wide motivation to the subject. So QCD is a theory that we understand very well at the two edges of the RG flow. Right? So at high energies, of course, thanks to asymptotic freedom, it is just a weakly interacting theory of quarks and gluons, SUN gauge theory with NF fundamental fermions. And at very low energy, if we assume confinement and chiral symmetry breaking in the usual way, then we know that the low energy theory is described by SUNF non-linear sigma model with a level n Wess Zumino term. And also, when n goes to infinity, S goes to 0. Well, by this, I mean that in the large n limit, U1 axial becomes a good symmetry, and the eta prime meson becomes an approximate Goldstone boson. And the way to add it to the theory is promote the SUNF target space to UNF, and then the eta prime is just the phase of the U1 part of this matrix. Well, this theory is very successful, of course. It is almost completely fixed by very nice theoretical arguments such as symmetries, anomalies, topology, and it reproduces many, many important theoretical and experimental results. Now, all the part in the middle, we don't understand very well. And for example, if we raise the energy a little bit, we find, in addition to pions, a zoo of mesons. There are a lot of particles, a lot of interactions. The space of parameters is huge. And this is not a place for theorists. But if you want to know what the theory is, you really need to go and measure things. We would like to have a nice theoretical argument that maybe reveals some hidden structure in this zoo of mesons and restrict the space of couplings in some nice way. So today I'm not going to talk about the entire zoo of mesons, only about UNF vector mesons. So in the terminology of phenomenologists, these are the rho and the omega mesons. I will denote them collectively by V in this presentation. And when writing the effective theory for the vector mesons, there are two observations or phenomenological principles that are commonly used. These are hidden local symmetry and vector dominance, which I will review soon. And these two principles are very nice in the sense that they give this extra structure to the vector mesons and restrict the space of couplings in some nice way. But they don't have any good theoretical explanation behind them. We don't understand why they are correct. So recently, there was a conjecture by these people and also by myself that the vector mesons play a special role as a Chern-Simons field on various QCD objects such as domain walls, interfaces, and one flavored baryons that were introduced recently 2 years ago by Zohar Komargodski. And what I want to show today is that, at least in the large n limit, this conjecture is intimately related to vector dominance and also to hidden local symmetry. And there are two ways to tell the story, two directions. There's something in the chat.
Oh, you can ignore that. Just talking about the recording.
If there are questions, then ask. Yeah. I will not look at the chat. Okay, so there are two directions to tell this story. So one direction is from experiment to theory. If you assume that hidden local symmetry and vector dominance are correct, you can write the effective theory consistent with them. And from this effective theory, you can derive the emergent theory on domain walls, and you will find Chern-Simons terms, the Chern-Simons terms that you expect to find, where the Chern-Simons fields are exactly the vector mesons. You can also compute corrections to the Skyrmion current. And these corrections, the full baryon current that you compute in the theory of both pions and vector mesons will reproduce the full spectrum of baryons, including both Skyrmions and also these one flavored baryons that I mentioned. So in that sense, this gives an experimental proof for this conjecture. And the other direction is from theory to experiment. Let's assume that the conjecture is correct and write the theory that will give us the expected domain wall theories with the correct Chern-Simons terms and the correct baryon current, then vector dominance is automatically satisfied. So this direction.
I'm sorry to interrupt, but what means baryon current? Current for what?
Current for U1 baryon. So you have the Skyrmion current plus corrections that you can compute. I will show you exactly what I mean.
Okay, I will see it. Yeah, because you mean baryon current is an interaction of vector meson with baryons, or the source of this baryon current is the source of what?
Yeah, the baryon current is I couple the theory for background gauge field for U1 baryon, for example. So I will have A mu, J mu, and this J mu is the baryon current. In the theory of just pions, it is the Skyrmion current. But when you include also vector mesons, you have corrections, and these corrections capture the one flavored baryons, which are not captured by the theory of only pions.
Okay.
So this direction gives a theoretical explanation to vector dominance. So a summary of the main results and also the outline of this talk is drawn here. So I will start from explaining the hidden local symmetry principle and what I call the hidden Wess Zumino action. This is the generalization of the Wess Zumino action that includes also vector mesons. This will be the main player in this game. And then we will see how these three concepts follow from the hidden Wess Zumino action. So first, vector dominance. This will be very fast, very short. Then I will show how to compute the corrections to the Skyrmion current and how the full spectrum of baryons is reproduced from this current. And then we'll move on to domain wall, QCD domain walls, and we'll see how the Chern-Simons terms are indeed appear when we include this term with the correct coefficients. Okay. So let's start from this hidden local symmetry in vector mesons. So how do we add vector mesons to the chiral Lagrangian using this idea of hidden local symmetry? So we have the matrix U. You take the Largen limit always. U is UNF valued, not SUNF. And what we can do, we can write it in a redundant way as a product of two unitary matrices, psi left dagger times psi right. And this transformation psi goes to H psi is of course a redundancy of this description, and we can couple it to dynamical gauge fields. And then we can write the action which is consistent with this new gauge symmetry, hidden gauge symmetry, and of course with all the other symmetries of the problem. So for example, at the level of two derivatives, this is the most general Lagrangian that you can write. We have the usual kinetic term for the pions. Here we have the usual kinetic term for gauge fields. And this term A here is a free parameter. In the real world, it is 2 for a very good approximation, but it is a free parameter. And this term gives us, of course, interactions between pions and vector mesons, but it also gives us a mass term for the vector mesons. So they become massive through the Higgs mechanism. So at the end of the day, the vector fields eat half of the scalars, the fictitious scalars that we add here. And the physical spectrum contains UNF non-linear sigma model, just the matrix of pions and eta prime, plus UNF massive vectors.
But it can, V mu, it is just vector meson or axial meson as well?
So I'm not talking about the axial meson, the axial vector meson. These are the vector mesons.
No, usually people consider, you know, early on it was about both. It was vector dominance, but it was both vector and axial vectors. And it was the more widespread effective Lagrangian for low energies.
Yes, so yeah, I have nothing to say about other mesons. Yeah, I restrict. You might worry that. How can
the reason I'm asking, because actually at that time, you know, because of the old age, I'm sorry. I mean, I remember this still. It was in particular discussion, you know, relation between, say, vector and axial vector, for example, that ratio of masses square was like 2. You know, it was a lot of stuff, activity associated with considering, you know, this kind of low meson A1, you know, and pi, and you know, this effective Lagrangian. I'm sorry, okay, but it's just
it's good that there are many more things. I'm just focusing on this part of the Lagrangian. I'm ignoring everything else.
Can I ask a related question though? I'm sorry to stay on this issue. So it is meaningful to only keep pions at low energies, but once you add the vector mesons, what justifies systematically neglecting everybody else, of which there's an infinite number of interesting mesons at large n, for example? So what will justify neglecting everything except the vector mesons?
Yeah, this is an excellent question. And so I don't have a good answer. There's no like scale separation between them and other mesons. And so I think that the main thing that we will see from here, first of all, there will be for vector dominance on 3-level diagrams, which are really, you don't need the other meson for them. And also for the domain wall, the Chern-Simons and the baryon current, you need this topological part of the action, which is, I think that you can ignore, there will be a lot of quantitative corrections to many things, to the baryon current and to the domain wall theories, but I think that the topological part will just get contributions from these vector mesons. No, maybe I'm wrong,
but look, you know, this idea about this axial vector, whatever, was that it's very simple. That you're saying that there is low meson dominance for vector current, and there is A1 and pi meson for axial current. You know, that's why it came together. You know, so it's and this ratio of masses, whatever was related to, you know, role of pi relative to vector and to axial. You know, okay, but no, I don't mind what you are doing. I just trying to recollect this, that it was natural to include this.
Yeah, I totally agree. I think that the term that I will focus on is just get contributions from the vector meson, like the topological part. You cannot write this Chern-Simons term for axial vector meson. It violates the symmetry, the parity. So it won't work. So this construction will not. The rest of the talk will not work for the axial vector.
I think this was originally due to Yamawaka, right? There is a person, a physicist in Japan, who considered this hidden spontaneous breaking of the gauge symmetry for vector mesons.
No, but Misha, it was early on. It was also Schwinger, for example, Weinberg. You know, so it was pure. No, I'm not sure who was the first, but it was very, very early on. You know, when we doing this soft pion, you know, it appears, you know, in this era. You know, so the idea to include vector meson was very early on.
Okay. No, but not just to include vector meson. It's two different ideas. You include vector meson because of apparent experimental.
No. It was together. It was together with dominance right away. No.
Yeah, I understand dominance, but the idea to make then the mass for the vector meson due to a spontaneous breaking of some hidden symmetry. I believe that it was.
Look, it's No, Mish, it was immediate part of this vector dominance, because when you are writing this, you are automatically, you know, kind of implying this, no, without mass storm would be no dominance.
Yeah, I understand, but it's not worth arguing.
Yeah, no, it's not about arguing. I'm just trying to say that it is, no, I do not know details, but my impression was that I do not think that this Japanese was first. It's what I'm trying to say.
Maybe he was not. Okay, maybe I'm mistaken.
I don't know about the history exactly. I will tell you.
No, it's your advantage to be young.
Yeah. Okay. So yeah. So I will move on if there are no other questions. So now, as we generalize the two derivative term to include vector mesons, we can also generalize the Wess Zumino term. So we can add to the Wess Zumino term the most general action, which is consistent with all the symmetries, and in particular this hidden gauge symmetry. But odd under the intrinsic parity U goes to U dagger, or equivalently psi right and psi left are interchanged. So the most general action can be written as follows. We have some normalization factors, sum over Ci, Li. Ci are just free real numbers that parameterize the theory. And Li are written here. So F is the field span for the vector mesons. RD and LD are covariant derivative of psi right and psi left, multiplied by the daggers on the right. And I'll just comment that I wrote here only single trace. There's an implicit trace here in flavor space. And I wrote only single trace operators, which is justified in the larger limit, but finite n, of course, there can be corrections to this Lagrangian.
But my impression was that, you know, in certain sense, Wess Zumino term is not with arbitrary coefficient, right? If you're following, you know, kind of Witten consideration or whatever, you have particular, at least some part of it should be fixed, right?
So this is in addition.
Yeah.
This is in addition to the Wess Zumino term with level n, with quantized coefficient. These terms don't carry any anomaly. They don't contribute to Tufte anomalies or something like this.
Then I'm a little bit lost. So it's not a normal Wess Zumino term, which was, for example, kind of for it's on top of normal Wess Zumino term, or what?
Yeah, and it has free parameters. It doesn't contribute to anomalies.
I see. You know what I was. Okay, I got it. So it's besides normal Wess Zumino term, you have those terms.
Yeah.
I see.
So can I ask a stupid question? So are the CIs completely unconstrained, or do they have to be integers, or what?
So there are no theoretical constraints on CI.
But then
I will try to give them constraints.
Okay. How do you know that the overall coefficient is n?
This is just a normalization factor. I can put in whatever I want.
Oh, I see. So it's not forced on you by something. You're just normalizing it by convention.
Yeah.
Okay. Thank you very much. I see.
Okay. So now we have these three terms, and if I couple the theory to some external U gauge field, which acts on the psi right and psi left, as written here, Q is the generator, the U generator that I choose. Then I have a freedom to add another term to this Wess Zumino action with coefficient C4. So we have over four free parameters in this theory. This U1 field can be background field, for example, a background field for U1 baryon, and it can also be a dynamical field such as the photon.
But I'm sorry, by dimension, all those terms are the same dimension as Wess Zumino term, or what?
These are 4-dimensional integrals.
No, but I mean dimension of operators are the same dimension of operator as a normal Wess Zumino term, or you know?
Yeah, they're dimension 4. They're marginal.
Yeah, I see. So all of them are dimension.
Currents are dimension 1. This is written on the right. So currents are dimension 1, and these guys are fourth order in the current. So dimension 4, dimension.
Okay.
So the CI are dimensionless. They are pure numbers. Okay, so now vector dominance. So the Wess Zumino action, including these corrections and coupling to the photon, is the part of the action that is responsible to all the processes that are odd under the intrinsic parity, because these are the only this is the only part that violates this intrinsic parity. Examples for such processes is the decay of pi 0 to 2 photon, decay of omega meson to 3 pions, and there are many more. The meaning of vector dominance in this context is that certain vertices don't appear explicitly in the Lagrangian, and therefore the related processes are dominated by an exchange of some intermediate vector meson. So for example, if we take this process of omega goes to 3 pions, naively we have this leading diagram, which is just the direct vertex of a vector and 3 pions, plus this diagram with intermediate row meson in the middle, plus many more.
No, but I'm sorry, but when you're adding this row meson exchange, let's take the limit where row meson is heavy. Then it's a part of the same diagram, right? So you are talking about next order terms in expansion in momenta. Let's consider momenta of pi to be small, right?
Yes, exactly.
So it's
these are corrections in E over the mass of the vector mesons.
Yeah. So it's I see. Next order in momenta. I see.
Yeah, exactly.
Mm-hmm.
So maybe this diagram is dominant, and but vector dominance means that this diagram doesn't exist, and then the leading term is this one,
mm-hmm.
the statement of vector dominance, and the type of vector dominance that we'll consider here, which is consistent with experiment so far, is that these three vertices don't appear in the Lagrangian, their coefficients vanish. So pi photon photon, pi photon vector, and pi 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 vector. And these three vertices vanish if these three conditions on the parameters of the Wess Zumino action are satisfied. So C3 and C4 equals 1, and also C1 minus C2 equal 1. So we still have one free parameter, but three of them are fixed. Oh, so this was a very brief review of vector dominance.
Right, can I check my understanding? Usually pi to 2 photon is driven by the anomaly, right? So it's coming entirely from the standard Wess Zumino term.
Yes.
Chiral Lagrangian. So you're saying that if you
Alex, but you know, he wrote vector dominance in such a way that in the limit where momenta are much smaller than mass of row, you are back to original vertex.
Exactly. This is very important.
Yeah. So you see, so it's normalized this way.
It gives you correction.
Yeah.
Beyond, above this dπr limit, which is controlled by anomalies, and Witten already wrote it. You have corrections which in energy over the mass of the vector mesons.
I see. And you want to make them strictly, you want to tune these coefficients in the way that you just wrote, and then there are no such terms? Is that the point, or what?
So the direct vertex of pi gamma gamma will not appear, but this process will still, the result will be the same result as the anomaly plus correction, because the leading, at low energies, if you integrate out the vector mesons, you go back to this original result.
No, just photons are going through row meson, so that's it. I mean, it is vector dominance, right? So you're saying that completely photons are not coupled directly, but coupled through row meson.
Yeah, but I just wanted to emphasize that it doesn't violate the thing that will already known by anomalies.
I understand the model now. Okay, I see.
Okay, good. Okay, so now let's move on to the next part, which is more interesting. This is the idea of the baryon current. So first of all, let's remind ourselves how to derive the baryon current in the theory only of pions. So we can show that the baryon current can be derived from the Wess Zumino term. And the way to do it is as follows. So we can compute the current for some general U1 symmetry that acts on U as written here. So this is a vector like a non-anomalous symmetry. And at the end, we take the limit Q goes to 1 over N, so proportional to the identity matrix. when we take U to be the identity matrix, U is invariant under this transformation, obviously. U is not charged under U1 baryon, but still we get an untrivial result for the current. And the current that we get, do you hear me? Yeah. Okay.
Yeah, we lost you just for a very brief second, but I think it was fine. Yeah.
Okay, I'm back. So the current that you get is the skyrmion current. And the charge configurations are well-known solitons called skyrmions, and these are the low energy description of baryons, and this current, S, is the low energy description of the baryon current. Now, a puzzle that exists about this skyrmion current is that the construction of skyrmions work only when the number of flavors is 2 or larger. If we have only one flavor QCD, then the skyrmion current identically vanish. And there are no skyrmions. We don't have the right topology to construct skyrmions. There was a puzzle. What happens? How can we describe baryons in one flavor QCD? So I will go back to this puzzle in 2 slides. But before this puzzle, let's repeat this procedure for driving the baryon current when we include also the Wess Zumino, the hidden Wess Zumino action, these additional parts that include also the vector meson. So we can derive the baryon current in exactly the same way. So we compute it for some global U1 that acts on psi left and psi right, as written here. So this is the global part. And I also choose to accompany it by some gate transformation. So this is gate transformation. This is convenient because at the end, when we take U to be the identity, proportional to the identity, psi left and psi right themselves are invariant. They're not charged under U1 baryon. So we can expect that only soliton or extended objects will be charged under it. So when we do this procedure, we get a full baryon current, B, which is S, the skyrmion current just from the usual Wess Zumino term as before, plus this correction, which is proportional to H minus S, where H is the current that is written here.
I'm sorry,
so,
aside, but when you are considering this construction, then and you have this UN symmetry, not as you know. So in this way, this eta prime, what about this U1 meson before baryon current? It is your U1 meson would be heavy indeed in the carry limit, or so this Wess Zumino terms account for non-zero mass of eta prime.
So you have also the mass term for the eta prime, which is 1 over n suppressed.
I see. So it's so it's separate. It's not part of construction by itself.
Yeah, this is only. Yeah, there will be corrections in finite n of double trace operators and so on, but I'm considering only the single trace one.
I see. So in this way, your eta prime is masses, right? In this sense.
Yeah, it's masses are very light.
Yeah. Okay.
Yeah.
Okay. Thanks.
Yes. So it is part of U, and Xi also has a U1 phase.
Yeah. It's what. Okay.
Okay. So we have this correction H minus S. H is this current. It looks like a gauged skyrmion current for psi right minus gauged skyrmion current for psi left, and it is also topologically it is identically conserved. And in order to understand what this correction means, we need to understand what is H, what is the relation between H and S. So H versus S. So first of all, you can check that when you integrate out the vector mesons, H just go back to S. So this correction vanishes at the low energies much below the mass of the vector mesons. The baryon current is just the skyrmion current. This is consistent. Also, the difference H minus S is a full derivative, and it means that the contribution of this correction to the charge will be 0 when you compute it on any smooth configuration. So these two are very important because they tell you that all the results that we already know about skyrmions not, they will still be correct. Nothing will get wrong with skyrmions. All the skyrmions will have the correct charge, and so on. So for sure, it is consistent from the point of view of skyrmions to use this, to add this correction to the baryon current. Now, what is the physical meaning of this correction then? It is, the charge is 0 for smooth configuration, but it can be non-zero for singular configurations. And an example for such singular configurations is the one flavored baryons that were introduced by Komorgodsky 2 years ago. So what are these one flavored baryons? So one flavor QCD contains, in the larger limit, contains only eta prime, and which is a periodic scalar with periodicity of 2 pi. And we can construct a configuration with this finite eta prime equals pi disk. Okay, so if we go through the disk, the value of eta prime changed by 2 pi. If we go around the disk, it remains 0 all the time. This is like a finite domain wall, in a sense. So another way to say it is that we have here the dashed ring, which is the boundary of this disk, and eta prime winds around the ring. As a result, the value of eta prime is not well defined on the ring, and we expect the chiral condensate to vanish on the ring. And in this sense, this configuration is singular. Now, it was conjectured that on this eta prime equals pi disk, there is an emergent U1 level and Chern-Simons theory. So we will go back to this conjecture later when we'll talk about domain walls. But now let's assume that this conjecture is correct. Then this system behaves like a Chern-Simons theory with a boundary. And as in the quantum Hall effect, we can expect to find a chiral edge mode living on the boundary, which is characterized by the winding of the holonomy of the vector meson, of the vector field along the ring. So here I chose the letter omega for the Chern-Simons vector field because I'm going to identify it with the omega meson, but at the moment it's just the Chern-Simons field which is emergent on the surface. So I have this configuration with eta prime and some U1 level Chern-Simons field, and the charge of this configuration is given by the product of 2 orthogonal windings, the winding of eta prime around the ring and the winding of the vector field along the ring. So the charge, the expression for the charge should be integral d eta prime wedge d omega with this normalization, 1/4 pi, plus or minus, which I didn't fix at the moment.
But why 4 pi, not 4 pi square?
So
It should
4
be
pi squared. Yeah, it should be 4 pi squared. Yeah, it should be 4 pi squared. Sorry, typo. And also here, it should be 4 pi squared. Let me verify. Let me, in a minute, just see in the paper that. Yeah, this is just a typo. It is pi squared. Yeah, sorry. Okay. So yeah, that's what this is the charge. This is what we expect to be the charge of the baryon. And now let's go back to the baryon current that we derived from the action. So the skyrmion current vanishes for NF equals 1. We already saw this, but H doesn't vanish, and therefore the full baryon current is not 0. If we write it explicitly for NF equals 1, it takes this form. So this is exactly the form that we want for the one flavor baryon. If this coefficient C3 plus C4 equals 2, or minus 2, but 2 or minus 2, and if we identify the Chern-Simons field with the omega vector meson, because this will get a charge when the omega meson winds around the ring. And this is consistent with the conditions for the vector dominance.
Before you mentioned the skin mesons starts from NF equal 2, right? And here NF equal 1, it's not, so it's not normal skin meson in this sense, or what?
It's not a skin meson, it is this object, which is made out of eta prime and some Chern-Simons vector field, which is emergent on it.
It's a pancake, you see?
Yeah,
if you
right.
try to visualize it, it's very thin, but its radius is not vanishing. So
right, but then we should see this pancake in the nature, or what? It's different from it's different from normal baryons.
In the nature, NF is 2 or 3, well, depending on your point of view about.
The claim is this is eta prime, you know. So this is eta prime. We see eta prime in nature.
So it's not a baryon in this way. It's meson, right?
No, it's a.
You mean delta plus
kind of a construction build of eta prime, right? And then you get a baryon charge equal plus or minus 1, but the corrected, expanded baryon charge.
No. I kind of lost.
It might be the delta plus plus if it is something, which is delta plus plus is like UUU. It is made out of only one flavor.
Yeah, you mean, okay, so isobar, you mean, right? So something like delta plus plus, it spins 3/2 usually.
Yes, yeah, the spin of this object is n/2. Zohar showed it explicitly in his paper. I
see. Okay, but so in this way, there are objects even in NF equal 2 or 3, which you can identify with these pancakes, or what?
I think that in the real world, it will be something more complicated because you have a massless quark, another massless quark, and so it will be some, and the eta prime is not, is quite massive. So it will be more complicated than this sketch. I don't know how exactly.
I see.
I also have a question. So you are at large N now, right? From here onward, you're always at large N, is that correct?
Yeah, until I will say that I'm not.
Until you say otherwise, okay. So aren't there a lot of stable vector mesons at large N? Because there are many, many resonances and they're all stable, and some of them have vector quantum, like they transform like vectors under SUNF, right?
Yeah, so I'm ignoring all the other mesons and I'm not just justifying it.
Okay.
Yeah, I'm just ignoring them. I have nothing good to say about.
No, but it actually implies that you could not go along Q square all the way, right? Because to reproduce, say, plus or minus two hadrons, for example, at large Q, one row meson would be not enough, right?
For what Q square? You mean?
No, let's say that you can see the plus or minus at like higher and higher energies, right? You can discuss, say, row dominance, for example, you know, at smaller energies, but then if you trying to produce high energy behavior, you know, you need it more, right? Than just vector dominance, or you know, or at least some special, you know. So it would be kind of much more complicated dynamics in the framework of row dominance, right?
No, but the standard vector dominance is valid only at small energies.
Right.
You go to high energies, it makes
right, but you see, it is because he is considering kind of corrections to it, right? Because it's so then you are trying to push yourself into the range of higher energies effectively, right?
Well, yeah.
Because
but
it's not just low energies per se. It is kind of you know, next terms.
It's next terms of expansion at low energies. That's
right. But then, for example, you can ask why rho prime, for example, would not contribute, or you know, so you can ask these questions, right?
So there will be a lot of corrections. So from the vector dominance point of view, the tree-level diagram. So the statement that the direct vertex disappear doesn't rely on this correction.
Yeah.
Just like, this is a statement about just the what naively will be the dominant vertex. Yeah. Okay. So yeah, if we write the baryon current for n equals 1, we have this expression, and we said that it looks like the omega meson should be this Chern-Simons field on the domain wall, and we also want C3 plus C4 to be 2 to get the correct normalization, and this is consistent with vector dominance, the condition for vector dominance that we saw before, that C3 equals C4 equals 1. So this is the first relation that we see between vector dominance and baryon spectrum. Okay, so I don't have a lot of time, so I'll move into domain walls. Probably I will not have time to say everything, but so now let's talk about domain walls. I will start from domain walls in an F equals 1 QCD, and we can draw the phase diagram of QCD in the complex mass plane. So the angle is the theta angle, and this is the theta equals pi line. And when the mass is very large, at theta equals pi, we're just at pure Yang-Mills. Theta equals pi, we have a domain wall, we have a spontaneous breaking of time reversal symmetry. And it was argued that the domain wall in this theory is U1 level n, or which is dual to SUN level -1 Chern-Simons theory. So this is based on the one-form anomaly matching condition. And so we know what happens when the mass is very large. We also know what happens when the mass is very small. Okay? So when m is much smaller than lambda, and in the larger limit, we can write an effective potential for eta prime. It includes two terms. So this term is it comes from the fact that U1 axial is not an exact symmetry. So this is it is 1 over n suppressed. And it is locally quadratic, but it has a cusp whenever eta prime equals pi, as you can see here. And this term comes from the mass term for the quark. So we can analyze this potential, and you can find that when theta equals pi and m larger than some critical value, which is proportional to lambda over n, this potential has two degenerate minimum points. And then you can study the domain wall that connects these 2 points. So in this picture, for example, we have these two minima, and the domain wall goes from here to here. And just explicitly from the Lagrangian for eta prime, you can find the domain wall theory, and it is empty. Everything is gapped here. So this led Gayotto, Komorgodsky, and Seiberg to give proposal for this entire line in terms of a U1 level n Chern-Simons theory coupled to a fundamental scalar. And there's also some fermionic description. And you can see that when the mass of the scalar is very large and positive, we can ignore it, and we're back at the U1 level n of pure Yang-Mills. And when the mass is very large and negative, everything is indeed gapped. You get the phi gets a vev, it Higgs says the Chern-Simons field. So you have a Chern-Simons Higgs U1 level n, which is indeed gapped. So they identified it with the phase over here. So now let's look at these domain walls more carefully. So we have actually two distinct trajectories to connect the two vacua, because eta prime is compact. We can go from here to here as we did before, but you can also cross the cusp. Now, in the regime where we can really trust the computation when m is smaller than lambda, this smooth domain wall has less tension than the cusp domain wall. So it is always the true domain wall. But we can still analyze this domain wall, at least as a metastable state. And we can ask what is the effective theory on it. Now, because of the cusp, we cannot read the theory from the eta prime theory by itself. We need to understand what happens on the cusp. So the common law for this cusp is that it is generated from integrating out some heavy fields that jump from one vacuum to the other as you cross the cusp.
But I'm sorry, just to follow that. Okay, do you have some kind of 2 pi periodicity in the picture?
Eta prime is periodic.
No, but I mean that in this way, here it is more than 2 pi, right? In your picture, right? So in this way, if I would say that I limit myself by 2 pi period, that say for example, it could be that going there, like I don't know, it's going to the same point as before, right? I mean,
you're right. This point is equivalent to this point.
Yeah.
2 pi periodicity, of course.
Yes, I extended it to emphasize.
Eta prime minus pi, eta prime plus pi are equivalent. I mean,
equivalent, right. So
this is the same point.
But then if I would say that, for example, the whole period is 2 pi, then, for example, I could say that this repetition of this is not needed, right? Then it is you go between these two minima over this without.
Maybe a better way to write is on a circle. You have 2 minima on the circle.
Yeah.
You can go from here to here or from here to here.
Yeah. Okay.
Yeah, this is what I meant.
Right, but okay, and then implies that spike implies that it is probability is much less, right there, right? I mean,
the tension is much larger.
Yeah. Okay. Sorry.
Yeah. So if we know what kind of field generated the cusp, maybe we can integrate them back in, write the effective theory for eta prime and these heavy fields, and then read the effective theory from this Lagrangian, that doesn't include the cusp. This is the idea. And we want to find a U1 level and Chern-Simons theory because on eta prime equals pi domain wall, we already said when we talked about the baryon that we need for the construction of the baryon to have a U1 level and Chern-Simons theory on this eta prime equals pi disk that we saw before. Now, how can we do it? So the conventional picture for this cusp is due to Divecchi and Veneziano a long time ago. So we can define this. Q is the topological density of the gluons. G is the field strength of the gluon. And we can write an effective theory for Q and eta prime. So eta prime Q is fixed by the U1 axial anomaly. And we can add a general potential or polynomial in Q, but in the Lagrangian limit, only the quadratic term is important and the other are suppressed. So from this theory, we can just integrate out Q and we get this potential for eta prime exactly with this cusp. So Q is the heavy field that generated the cusp in this construction. And we can also see that we can, from this coupling eta prime Q, we can indeed get the Chern-Simons theory on the domain wall. So if eta prime interpolates from 0 to 2 pi, this term will give us on the domain wall exactly SUN level -1 Chern-Simons theory, which is dual to U1 level n. So this is really what we wanted to get. So it works.
Right. Where do you see the Chern-Simons thing? I mean, I can see how this gives you the potential that you want. Where is the Chern-Simons coming from with this?
So Q is like D of Chern-Simons. And we integrate by parts. Let's take configuration where eta prime winds from 0 to 2 pi.
Okay.
So it is like the eta over 2 pi wedge Chern-Simons with level SUN Chern-Simons with level -1.
I see. A domain wall in eta prime ends up carrying the. I see. Thank you.
Oh, great. Thank you. So now we can look at this. Go back to the Wess Zumino action. Let's write it explicitly for one flavor QCD, and it takes this form when n f equals 1, and this is very similar to this eta prime Q coupling that we saw before. So eta prime now coupled to a topological density of vector mesons instead, the omega wedge the omega. And we take this coefficient C3, and if we take C3 to be 1, which is what we want if we assume vector dominance, then we get it here the normalization n over 8 pi squared, which exactly gives us, on the same way that we had before, U1 level n Chern-Simons theory on this eta prime equals pi domain wall. And actually it is Higgs because omega is Higgs. So it is a U1 level n Chern-Simons Higgs, but still we get this U1 level n Chern-Simons term from this Wess Zumino action. So what I want to propose now is that actually this is a dual description of the vacuum Veneziano. So this coupling to the vector mesons and this coupling to Q, they don't exist together at the same dimension, but there are two dual descriptions where the vector mesons are actually dual to the gluons. And this is motivated by the Chern-Simons duality on the domain wall that maps the SUN level -1 of the gluons to the UN level n of the vector meson. And the related consequence of this proposal is the conjecture that the cusp potential for eta prime in this description should be generated by integrating out the vector mesons. So this is something that I've still time to think about and to argue. This is some work in progress, even not work in progress, very initial project. But now we can go back to the domain wall. And so how much more time do I have, Alexei?
I think you can keep going. If people need to leave, they can ask questions before they leave, but usually we run a bit over, so.
Okay, so I will continue and tell me if I need to stop.
All right.
So now let's go back to this domain wall story. We have, this is the potential for the eta prime as we saw before, and the potential depends on the parameter, depends on the mass. When we increase the mass of the quark, it is modified from something that looks schematically like this to something that looks schematically like this. And we can assume, or we can guess that there is a phase transition between the two domain walls as we increase the mass. So there's some, in the regime where m is smaller than lambda, it doesn't happen. But it is very natural to assume that when m is of order of lambda or something like this, there will be a phase transition such that this domain wall will have less tension than this domain wall. And if this is correct, then it means that this domain wall is the one that is connected continuously to the pure Yang-Mills domain wall. When we start from Yang-Mills and reduce the mass continuously, we will end up on this domain wall, not on this one. And what are the evidence for this phase transition proposal? First of all, we found a U1 level n Chern-Simons Higgs on this cusp domain wall. So if you remember, Gayotto, Komogoti, Seiberg, they proposed this U1 level n, which is Higgs on the small mass side of the theta equals pi line, but they identify it with the domain wall here, which is just gapped. But to me, it seems much more natural to identify it with the domain wall here, which is indeed U1 level n Chern-Simons Higgs. And you can, another reason why this phase transition should happen is that, first of all, we saw that the difference between the tensions decreases as we increase m. We can compute it also in the regime where it is under control. And you can expect that the tension of this cusp will remain finite and independent of m when you take m to infinity. Well, the tension of this domain wall, you can expect that it will diverge and go to infinity as you take m to infinity. So it will disappear from the spectrum at large mass, and it will not be connected continuously to Yang-Mills. And there are several consequences of this proposal. So if this domain wall is continuously connected to the Yang-Mills domain wall, it means that as you increase the mass of the quark, omega actually becomes massless in the Yang-Mills limit. Oh, not always, just on the domain wall for theta equals pi. And in such a way that it transforms continuously from this bound set of quark-antiquark to some kind of glue ball in the Yang-Mills limit. So this is very similar. The ideas here can remind us the story of Seiberg duality between gluons and vector mesons. So we saw that we have this Chern-Simons duality on the domain wall that mapped vector mesons to gluons. And this is very similar to Seiberg duality between UNF vector mesons and SUN gluons. And well, okay. So the story of this Seiberg duality is, roughly speaking, as follows. So we start from SUN coupled to NF flavors, you flow down until at some critical point, you have a dual description in terms of UNF vector fields coupled to symmetric content, such as xi left and xi right. Now, this side has confinement. Here we have Higgs, and the two theories flow to the same chiral Lagrangian at low energies. So we can ask whether this duality is correct or how much is it correct. It's for sure correct at the deep IR because these two theories flow to the same chiral Lagrangian. And it looks like it is correct also a little bit above it because due to this hidden local symmetry principle, the vector field, the vector meson looks like a Higgs vector field. And we can ask whether it is also correct here, close to M star, whether V indeed become true massless gauge fields at some point. And well, these are very hard questions. I cannot answer them, but it looks like from this picture, from the Chern-Simons duality on the domain wall, and from the fact that omega becomes massless in some regime, this is not this regime, but this regime of a large mass at theta equals pi, it looks like maybe there is something into it, and it can be very interesting to explore it.
So I have a question here. So normally for Seiberg duality, the supersymmetry was important. So why do you think here, is there some symmetry also that's going to be important for this connection?
No, this is just a conjecture that exists in the literature in a couple of papers. And I think that all the evidence that we have for it are what I said. And the hidden local symmetry and the supersymmetric analog. But this is why I have a question mark here. I don't know.
So basically the duality you're saying really has nothing to do with supersymmetry. It's just that these two theories just flow to the same theory in the infrared. Just
in the sense that the flavor symmetry here becomes the gauge symmetry here, which is similar to Seiberg duality. Yeah, this is the only.
Yeah, I see.
Yeah.
Thanks.
So it is interesting if there is some structure of this type, but we don't really know. This is just a conjecture. Okay. So yeah, I have a little bit more. Now let's move on to domain walls in QCD with a higher number of flavors, so NF larger than one. So now similarly, we can draw the phase diagram in the complex mass plane. When the mass is large, theta equals pi, we have the Young-Mills result, the Young-Mills domain wall. When the mass is very small, you can explicitly find the domain wall from the higher Lagrangian. So you can find the configuration that minimizes the action, the energy, which will give you the domain wall when m is much smaller than lambda, takes this form, and it breaks the SUNF global symmetry to SUNF minus 1 times U1. So on the domain wall, you have this nonlinear sigma model, and the Wess Zumino term of the chiral Lagrangian will give you a level n Wess Zumino term on the domain wall. Now again, Seiberg gave this proposal for the entire line in terms of a U1 level n plus NF fundamental scalars and also some dual fermionic description. Again, when the scalars are very massive and with positive mass, we can ignore them and we're back at the U1 level n. When the mass is very large and negative, they get a VEV, they Higgs the gauge field, and they break the global symmetry exactly in the same way. So also here, in this theory, you find the same non-linear sigma model. And when you integrate out the massive vector field, the Chern-Simons term at low energies will just become a level n Wess Zumino term on the domain. So this indeed gives you the correct phase. And it relies on the assumption, first of all, that there's no phase transition between the domain walls. So this one is connected continuously to the Young-Mills one. And you get that the Wess Zumino term on the domain wall comes from integrating out a U1 level and gauge field. Now, using this idea of using this hidden Wess Zumino action, we can find the domain wall theory with the vector mesons now included. And what we will find straightforward computation that in addition to the sigma model, the sigma model will interact with SUNF minus 1 times U1 vector field. So some of the vector mesons will decouple, but these will still interact with the sigma model coordinates. And the full Wess Zumino action will generate on the domain wall this ugly term, very ugly expression, which some of it looks like a Chern-Simons term, some of it looks like a Wess Zumino term, and there are also other parts. And when you integrate out the vector fields, this whole mess just reduces to a level n Wess Zumino term as expected at low energies. So what you see from here is that, first of all, the Wess Zumino action on the domain wall is not generated from integrating out a U1 level n gauge field. It is generated from this ugly expression, which is different. So this is in direct contradiction to Goyoto-Komorgodsky-Seiberg proposal. And we also have the same arguments for phase transition between domain walls. So again, we can assume that this domain wall with the sigma model is not connected continuously to Young-Mills. Instead, this eta prime equals phi domain wall will be connected continuously to Young-Mills as we had before. So I'll just take maybe 2 more minutes. So far we discussed only the parameters C3 and C4 from the theoretical point of view. Because L1 and L2 in the hidden Wess Zumino action are identically 0 for one flavor QCD. We saw that when we choose C3 to be 1, it fixes the coupling between eta prime and FOHF to take this form. Now, if we want that when we add more flavors, we'll get the same form for the coupling between eta prime and FOHF, the correct non-abelian completion to this axion-like term, we need to choose. This happens only when C1 equals 2 over 3 and C2 equals 1 minus 1 over 3, and which is consistent again with vector dominance, surprisingly. According to vector dominance, C1 minus C2 is 1, which is indeed what we get here. It's also consistent with the non-abelian extension of this Chern-Simons duality on the domain wall. So now it will be from this term UNF level n dual to SUN level minus f. So it continues to work also at higher flavor QCD. So I'll just finish here. So yeah, just this summary of what I told you is that from the hidden Wess Zumino action with the vector mesons in the large limit, we saw that the conditions for vector dominance and the expected Chern-Simons terms on the domain wall and the correct baryon charge that will include also the one flavored baryon, the conditions for these 3 concepts coincide, and they give us a theoretical explanation for vector dominance in some sense. And there are a lot of open questions. For example, what happened at finite n? I think that this term should remain exact, and all the other terms should receive corrections, but this term should remain exact, but I don't know for sure. So it would be interesting to check in the real world, for example. I don't think that it is measured. And I gave some new proposal for the domain wall theory that includes phase transition between the domain walls. And there was some open question about Seiberg duality, Seiberg-like duality between gluons and vector mesons, and whether the cusp in this dual description is generated from integrating out the vector mesons. So these are some open questions that I hope to investigate more in the future. So thank you very much.
Thank you.
Thank you. We can thank you.
It's very interesting. I have a question. This, what you are saying about vector meson omega at theta equal to pi, which it becomes when it becomes massless. Do you mean it becomes massless in the bulk or just as a vector excitation on the domain wall? I didn't quite get it.
So on the domain wall, the minimal statement is on the domain wall.
Okay.
This is the minimal statement. Yeah.
Yeah.
Whether in the bulk it becomes messless, maybe.
Maybe.
I have no evidence for it.
Okay. Okay. So you discussed, do I understand you correctly? You discussed the phase transition between different types of domain walls, presumably in large N QCD with one quark, right?
Yeah, first with one quark and then also with two
So
more.
depending on the mass of the quark, at small masses, you have a certain domain wall. At large masses, it's a different domain wall, and there is a phase transition in the tension, right? Or
Yeah.
in what? Is it first order phase transition or second order, or what do you think?
If this proposal is correct, then it is first order, because you jump from this theory over here to this theory over here.
Uh-huh.
This is totally topologically decoupled trajectories.
I see.
First
I
order.
see. So it's first order transition. Interesting. Something similar exists in super Young-Mills theories. Of course, there are many different domain walls, and I even started discussing with Zohar, but because of this coronavirus, everything more or less stopped. Zohar has children to take care of.
Yeah, no.
When his wife is in the hospital. So, but it's something similar there. I also expect to have first order phase transition. Yeah.
Yeah, I talked to Zohar a lot about this first order.
Yeah.
I think that also, so from holography, people argue that it is first order, but I don't know much about it.
Okay. Yeah. Okay. Thank you. Anyway, very interesting. It's more or less corresponds to your recent archive submission, right?
Yeah, it is exactly the same. It follows this.
Okay. Thank you.
So sorry. So actually, I had a related. From what you just said about holography, is there a like a 5D description of what you're saying as well, or not? Do you think?
I don't know. I don't know. I didn't have, again, I had plans, but coronavirus changed.
Because
plans,
people
and I
look.
didn't have a lot of time.
Yeah, because people looked at this vector meson dominance. They constructed these models with gauge fields in the bulk, and they also noticed they explained this vector the meson dominance as well as the lowest KK. And so I was just wondering if maybe there's also a story where you can model these Wess Zumino terms and do a similar construction to what you suggested.
Yeah, I'm not sure. I need to investigate this holography story more carefully. So I know if you look at, for example, at Zohar's paper about this image, you will see that there is a reference to a future paper about holography that he will write with Ofer Aharoni and who else, where they claim that it works. The construction of the one flavored baryons works from holography, but they never published this paper. And from what I heard, they don't plan to publish.
Oh.
So I don't know. So something, I don't know.
I see.
There's something into it. Maybe. It works in investigating.
I see. Thanks.
So I also want to say that this is very interesting. It's kind of amazing that it all fits together so nicely when you add one vector meson. But so that really is fantastic. But I think from the point of view of QCD, this amounts to a very interesting model. That is to say, in real large N QCD, this is clearly not going to be correct, because there is an infinite number of vector mesons, and there's also an infinite number of other fields. For example, the axial vectors, which could change the results significantly. And for example, to me, it's not immediately obvious how to even imagine taking all of that into account, nor is it clear in what sense it could possibly be that it's somehow the effects are suppressed and so on. And yet, results are so nice that maybe somehow all of this other stuff really is somehow negligible or suppressed. So
I don't know if
so this
it's
is-
suppressed or just don't contribute to this topological part.
right, but then right. So that's right. So indeed, so it's very tempting to say that maybe what they will contribute to are like the details of the mass of a skyrmion or whatever.
Yeah.
Of course, cares about all of this, but for the topological stuff, maybe it doesn't contribute. But how it will fail to contribute is really not obvious, and it would be super interesting if it could be worked out. Like even if you just add one extra field.
No, but Alexei, if I can just say something here. I mean, I think something similar was also noticed when people did the 5D versions of this vector meson dominance, because there you also had this Kaluza-Klein tower, which is these resonances, stable resonances. And again, you would think that these other resonances would affect the low energy physics, but people noticed again that it was mimicking vector meson dominance.
But there was some non-trivial identities that forced this, right?
Exactly, yeah. But it was a consequence. Yeah, it was a consequence of putting this in the bulk. But again, it didn't depend on the fact that you had this infinite tau, which is what you're referring to.
But what did it depend on? The specific splittings between, like, was it a consequence of the specific details of the holographic models and their spectra?
Exactly, yeah. I mean, that there was from what I recall, is that it was just the lowest lying mode had the biggest effect.
You say empirically, the answer to this question is known. If you compare rho and rho prime is the first radial excitation of rho. The residue of rho prime, it will, let's say, electromagnetic current or vector current, is much smaller than the residue of rho. Not only its mass, its mass squared couple, it's 2 times the mass squared rho, but also the residue to the electromagnetic current is maybe 1/6 or so 1/6 and times 1/2, it makes it less than 10%. And higher excitations are still less coupled. Of course, if you come in energy close to higher excitations, the fact that they have smaller residues doesn't mean anything, because right at the point of the resonance, even if the residue is small, but the width of the resonance is not still so large. So at high energies, you feel indeed excited states. But if you have energies of order, let's say, less than 1 GeV squared or so, then the suppression of couplings of higher vector resonances, empirically at least, it solves the problem. But this should be then seen in any model, right? That the residues
Exactly. That's what I'm sort of dreaming, that if one takes this approach and builds in some tower, that you would get some constraint on the properties of that tower, in particular on the couplings, on the residues. Like there should be some there should be some interesting constraint on how all of that works, so that it does not screw this up. And that would be an interesting constraint on the behavior of large NQCD or whatever.
Yeah, it can be very interesting. I have no idea how to do it.
And can I ask one other question? So you were saying that you have this result for the omega going massless on your domain wall, and you were saying that it's conceivable that it also goes massless in the bulk at theta equals pi.
Yeah.
Is that right?
This is, well, the reason I said it is that I wanted to use it as kind of hand-wavy evidence for the Seiberg duality, where there is a regime where the vector mesons become massless. But it is not related. This is just, something that I have no evidence for it.
I see. It would amount to saying that QCD can become gapless at theta equals pi.
No, yeah.
The chiral limit. It sounds like very strong, you know?
Yeah, no, you're right. It should be on the domain wall. Only on the domain wall.
Yeah, the natural thing, the thing that's much easier to accept is just on the domain wall,
Yeah, I agree. Sorry,
Okay.
Young means that theta equals pi is not massless as far as we know.
At least as far as we know, I mean, but Yeah. Okay.
Oh, but you say you consider not just QCD, theta equal to pi QCD. It's a little bit different from our
True.
QCD.
That's true.
Right?
That's true.
Like for instance, if in CP models, let's say supersymmetric, no, supersymmetric are not useful. So in CPN models, we have confinement of the quote unquote quarks at arbitrary theta, but we don't have confinement at theta equal to pi. It's a conformal regime. So something of this type may happen.
That's right.
In the large unit, I think it is known that there's still confinement.
Yeah, so that's the subtlety. For n equals 2, yeah, people don't really know what happens to Yang-Mills at theta equals pi. There are arguments. Maybe it goes gapless, maybe not. But for large n, yeah, as Avner is saying, I thought the prevailing belief, at least, is that it remains a gapped theory with confinement and so on.
Well,
Maybe it's a belief, maybe we can find the hole.
And there was a paper this week arguing that from numerics that also for n equals to 2, there is confinement at theta equals pi. I don't know if it's correct or not.
Maybe, of course, it's not the case, but
Some lattice QCD.
Heplat. Okay. Okay. Very interesting. I should look because it's not so easy to simulate the theory at theta equals pi.
Yeah, I don't know what they did exactly.
Okay, I'll have a look. Very interesting. I missed it.
Okay, thank you. I have to go too.
Okay, I have to teach.
Thank you for a very interesting talk.
Thank you very much. It was lovely.
Okay.